Okay, midterm exam, spring 22. I know it happened some time ago, but for many of you it would be worth going over at least some of these questions, if not all of them. So I'm going to make this video just to review. The 3 multiple choice questions are found here in Moodle. So you can go there and you can see the answers. A lot of those selections were tricky, so many of you did not do well on those. But multiple choice questions are always a good way before an exam to review concepts such as electric field lines and conductors in static equilibrium. So just go back and take a look at those. There were 8 other questions, and I'm going to walk through those questions one by one. But the first question, the 4 charges and a point forming a square, was probably the one that was the most challenging for you. So I'm going to solve this in some detail because there's a lot of detail that you're neglecting. So we have 3 electric charges, a charge of 1 nanocoulomb, 2 nanocoulombs, and 3 nanocoulombs. All of those charges have electric fields, and so at this point there'll be 3 electric field vectors due to Q1, Q2, and Q3, and you need to draw those. So we're at point P. Don't draw anything here like that. That's the field line. That's not the vector at point P. The vector at point P, and it's not a field line, it's a field vector. This is E1, a field vector at point P due to charge Q1. You should not have an arrow there. The arrow should be here because it's the electric field at point P that we're evaluating, and that's going to be equal to the sum of 3 vectors. That's why you start with this statement. That's the important thing that some of you missed. So that's an important concept. We're going to point P. We're drawing the vector E1. We're drawing the vector E3. That's going to be 3 times longer because the charge is 3 times bigger. And it points away because they're all positive charges. And Q2 is going to point away from Q2. But because it's further away, it's not going to be 2 times bigger. It actually ends up being equal in magnitude to E1. So this is what your diagram should look like. There should be no arrows on the charges. There should be no arrows here. The arrow should be here. These are 3 vectors, and we have to add them as vectors. You cannot add these as numbers. That goes back to week 3, semester 1. This is important, and it's easy to forget. So this is what we're doing. So we have to get E1, E2, and E3 in component notation, IJK notation, and then add them. So let's do that. Okay, I cleaned up the screen. Here's the figure. I deleted a lot of other stuff. There are the 3 vectors we're adding. I forgot to label them. So what we're doing is we're getting the field here. The field here is the result of a field vector due to each charge, and we're adding vectors. That's missing the vector sign. So to find the vector E1, we have to find the magnitude of E1 and then find the components. So notice I write the equation down, and I use the absolute value signs because we're finding the magnitude. Then I put K, and in most cases we can use 9. You can use 8.99. It's just the numbers are a little more rounded, so I'm going to use 9 times 10 to the 9th Newton meters squared per Coulomb squared. Notice I got the number and the units. Okay, now here I have 1 nanocoulomb, so I have to put it in units. So 1 times 10 to the minus 9 coulombs, and then it's divided by the distance. That has to be in meters, so the 30 centimeters is 0.3 meters, and it's squared. So what am I going to do at this point? Just to make life easy, I'm going to let the 10 to the minus 9 and the 10 to the 9 cancel. So I have 9 divided by 0.3 meters squared, which ends up being 0.09. And so this ends up being exactly, if we use 9 for K, 100 newtons per coulomb. So that's the magnitude. Now we can see from the figure that E1 has no y component. The angle of this is 0 degrees. So what I would do is just quickly go and write down that E1 equals 100 newtons along the x-axis I-hat direction plus 0 newtons per coulomb in the j-hat direction. And I'm not going to list the k-hat, but you could write 0 in the k-hat direction. Now this would come out of, if I wanted to do this out, it's really not necessary because it's clearly only an x component. We would write E1x equals E1 cosine theta, and the cosine of theta is 0, which is 1. And the y component would be E1y, would be E1 sine theta, and the sine of 0 is 0. So, but in this case it's obvious, right? We don't really need to do the calculation. And now, just moving along, if we look at Q3, we can see that's in the y-hat direction, and the j-hat, or along the y-axis, positive direction. And so when we do this, everything is going to be the same except Q3 is going to be 3 times bigger. So we end up, let me erase some things. Okay, I hope you're following. So we're adding 3 vectors. E1 is 100 newtons, 0, right? No y component. E3, that's the other easy one. It has no x component. It would be the cosine of 90, which is 0. And the sine of 90 is 1. That's 3 times bigger because the charge is 3 times bigger and the distance is the same. Now this distance is greater. This is, right, if this is s, this is the square root of 2 times s, this distance. So I have the square root of 2 times 30 meters. It ends up being 42 point something centimeters. If you want to calculate it, that's fine. I'm just writing it this way. So when I square this, the 2 is going to square to a 2 and cancel that. Notice the units. I didn't go over the units last time. I put in all the units, right? But notice what happens. This is a meter squared, so it's going to cancel that meter squared. And there's a coulomb here, which will cancel one of those coulombs. And that leaves the units as newtons per coulomb. So anyway, you can do this calculation, and you'll see that when you do it, you get 100. But we need the components. So this ends up being 100 newtons per coulomb. But now the angle is 45 degrees. So let me make some space. So we have the magnitude of E2 is 100. I didn't put the numbers down. This is 100 newtons per coulomb. And the cosine of 45 and sine of 45 are the same. So we get these values for the components. It's 45 degrees, so the components in the x and y direction are equal because the sine and cosine of 45 degrees are equal. So we can put that for E2. We get 71 newtons per coulomb. Oops, I messed up these units. You see, it's easy to get field and force confused. These should all be newtons per coulomb. Plus 71. I'm rounding to two significant figures. That's good enough here. This is I hat. This is j hat. And oh, I messed up these. This should be I hat. This should be j hat. I'm going too fast. And then we add them all together, right? This is, remember back in week 3 when we did vectors, we made tables of x and y components, right? So think of this as a table, and this is how you should think about it. And then you add these, and you're going to get 371 newtons per coulomb in the j hat direction, and 171 newtons per coulomb in the I hat direction, and that is E total. That is E at point P. That's the vector, the two components, and that's all you had to do. But you should know how to get the magnitude and direction. So remember, the magnitude, if we want to know what's the magnitude of this vector, right, it's going to be the magnitude of any vector. Writing the notation for magnitude is the square root of the x component squared plus the square root of the y component squared. Right, this goes back to week 3, semester 1. You've got to remember these equations for doing vectors. And so this would just be the square root of 171 newtons per coulomb squared plus 371 newtons per coulomb squared, all that squared. And then when you take the square root, you get 408. I think that's the number. 408 newtons per coulomb. That's the magnitude, right? It doesn't have a direction. But the direction you would get, remember, inverse tan of the y component over the x component. So it's going to be the inverse tan. Now all this writing, I'm getting a little messy because I don't want to keep erasing and changing screens. All this writing is what should have been on your exam paper, except this last part, right? I didn't ask for this. So the theta would be, it's getting a little messy, but I don't want to erase, so we would have the 371 newtons per coulomb over 171 newtons per coulomb. Notice the units cancel, and the inverse tan of 371 over 171 is about 63 degrees, if I can remember correctly. So there's a lot of work there. There's a lot of work to show, and there's a lot to remember about vectors. And some of you remembered, some of you didn't. This is a good review, though. And we now have, in our current assignments, right, we have magnetic field problems that are very similar to this. And so likely on the final exam, I'll include a problem similar to this, but involving magnetic fields. Actually, we're not done. This is parts A through C. Now we're asked for this arrangement, this square arrangement, we're actually calculate the potential here. So let's do that. Okay, so we're switching concepts here, and it's important to pause and remind yourself when we're talking about electric field, each charge has a field which goes away from it. So at this point, the field is a vector in that direction. Here the field, so the field is a vector, and the field is the force per unit charge. So field is related to force, but potential is related to energy. The electric potential is the electric potential energy per unit charge. So it's useful to keep the parallels and differences between these concepts. So when we go to this point, we're asking what's the potential energy per unit charge at this point. And there's an energy there due to all three charges. But they're not vectors, they're energies, they're just numbers, they're scalars. So the total potential at P is going to be the sum. And there's an equation for that, right? The equation for V1, V2, or V3. V1 is going to be K Q1 over R1. It's not squared, it's almost the same equation, but this gives us an energy and not a potential. And so on for Q2 and Q3. And so on your exam, you should have this equation, and then you should show each individual equation. You should write the numbers down. 9 times 10 to the 9th Newton meters squared per Coulomb squared. What's Q? 1 nanocoulomb. 1 times 10 to the minus 9 coulombs, and then we're going to divide it by R, has to be in meters. 0.3 meters, not squared. Notice now we have 1 meter canceling 1 meter here, and 1 coulomb canceling one of these coulombs, and that leaves us with Newton meters divided by coulombs. A Newton meter is a joule, so that's joules per coulomb. That is the units. Those are the units of potential. And once again, just to make calculations easy, there's a 10 to the 9 and a 10 to the minus 9. They cancel, and that leaves you with just 9 times 1 divided by 0.3. And so this value would be 30 joules per coulomb. So this is 30. This is 3 times bigger, same distance. This is going to be 90. And here you have to use this distance, which is about 0.42 meters. And when you do that, you'll get something about 42 here. And so the whole thing ends up being about 162 joules per coulomb, or volts, right? Unit of volts. Okay. Now, if we put a charge here, this is the easy part if you know what to do. If we put a charge here, it's going to have energy, right? There's 162 joules per coulomb of energy potential associated with this point. So to get the energy at this point when a charge is there, we simply use this equation, that the energy is going to be the charge times the potential. So you just have to multiply the 4 times 10 to the minus 9 coulombs, I don't want to write it all out, times the potential, 162 joules per coulomb. You see the coulombs cancel and we get joules. And the last question is the force. So the force is simply Q times the field. So you put the 4 times 10 to the minus 9 coulombs here and multiply by the answer you got for the field in part C, and that gives you the force on a particle placed in this position due to those 3 charges. That's how you should be thinking about it. Now, if you're still confused about any parts of this, you should ask me. We should go over it. Come to my office hours and let's talk about it. Okay, we spent almost 20 minutes answering question 1. Let me just step through the other 7 questions and make a few brief comments. To understand flux, you need to understand field. And I think it's important to be able to visualize fields. That's why we have field lines. And it's important to remind ourselves that these fields are static, right? There's not things like a light bulb emitting light. This field is a static field, and we represent it like this. And field lines go from positive charges and end on negative charges, but there's nothing flowing. But we use the word flux because it appears to be a flow. So flux, in a picture sense, is the number of field lines that pass onto or through. It doesn't have to go through the surface. Flux can be onto a surface. Sometimes field lines terminate at a surface. Sometimes they pass through a surface. So so that's your statement, right? The electric field onto or through a surface. And so to calculate the flux onto or through a surface, it's going to depend on obvious things: the strength of the electric field, the area over which we're collecting the flux, or the flux is passing, and the angle between those two vectors, right? So the cosine of the angle between those vectors, that's why we can write it, if you know the dot product, E dot A. But if we want to generalize it for any situation where the direction of E or A or the angle between the E and the A vary, then we do it as an integral. So the amount of flux, or the number of field lines, or the amount of field lines onto or through a surface, is going to depend on the field strength, the area of the surface, and the angle between them. That's why we write it as a dot product, EA cosine theta. And you should have a figure to illustrate that. If the area is bigger, you get more flux than if the area is smaller. If the field is stronger, you get more flux than if the field is weaker. And if the angle is 0 degrees, right, it's the direction this is facing the same direction, then the flux is less when the angle is not at 0 degrees. So this illustrates all those. Of course, the definition from your equation sheet, which you absolutely should write down, it should be one of the first things that you write down, would be in the general situation, because the E or the A or the cosine of theta can vary from point to point, would be the integral of E dot dA, writing it as a dot product, or the integral, since it's a surface area, it's a double integral, E dA cosine theta. So your answer should have the equations, should have some language like I just said, and should have at least one diagram like the one I drew. Now when we move to Gauss's law, that's often confused. Gauss's law is related to flux, but it's the relationship between the electric flux over a closed surface. So this is the definition of electric flux over a closed surface. It's equal to the charge inside the surface divided by that constant epsilon naught. So this is flux through a closed surface and what it's equal to. So Gauss's law is a relationship between flux through a closed surface and the charge inside the surface. And so oftentimes people say, oh, we can use it to find flux, or we can use it for those things, but what it is it's a relationship. Flux is a definition of something, the amount of field or the number of field lines onto or through a surface, Gauss's law is a relationship between flux through a closed surface and what's inside the surface. And you need a diagram to explain that. So here's a nice diagram. It's good to use this one. So I've drawn a dipole, and we know about field lines. 8 field lines leave the positive charge, 8 field lines enter the negative charge. So we can picture the field. And if we draw, let's say, a closed surface, an imaginary circle in 2 dimensions or sphere in 3 dimensions, the green one I'm going to call S1, surface 1. And this could be a real or imaginary surface, but I'm making a surface here. I'm making a surface 2 here in red and another third surface in blue. And if you notice, surface 1 has 8 field lines going out and no going in. So 8 field lines, we could say it has a flux of 8. So the flux through surface 1, closed surface 1, is 8. I'm counting field lines. It's proportional to the flux, right? The flux through surface 2, there are 2 field lines going in and 2 field lines coming out. So the net flux through surface 2 is 0, and there's no charge inside. Now I've drawn the blue, surface area 3, so that it splits the charge in half. And so what you'll see is, you'll see 4 field lines entering and none leaving, right? The field lines terminate inside the surface. So 4 field lines go in. So what's inside there? A negative charge of half the magnitude as the green surface. So that shows the relationship between closed surfaces and Gauss's law. Yes, we use it to find charges inside. Yes, we use it to find flux. But the relationship is that if more field lines go into a closed surface than leave, there's a negative charge, a net negative charge inside. If more field lines come out of a surface than enter, then there's a net positive flux. There has to be a net positive charge inside. That's the essence of Gauss's law. And so the statement, the equation statement should be there, and a figure and some words explaining it like I just did should be part of that answer. Okay, Kirchhoff, 2 laws. So the voltage law, Kirchhoff's voltage law, Kirchhoff's current law, also known as the loop rule, this known as the junction rule, a junction or a node, a place where wires meet. And the equation, you should write the equation down and the name. So all this should have been in your answer. The sum of voltages around a closed loop, you have to specify a closed loop, equals 0. That's just a statement of conservation of energy. The energy that the power supply puts in has to be equal to the energy that the resistors or the devices use. This is called the loop rule. The junction rule, currents in equal currents out, or the sum of the currents in a junction. Entering is positive, negative, exiting is positive. They're going to sum to 0. Same thing. Kirchhoff's current, the junction rule or the node rule. And it's based on conservation of charge. Now we use these to write equations to solve circuits such as the one you were given in the exam. So the way we solve Kirchhoff's circuit problems is similar to, but in some ways a little bit different from what you might learn in circuits. So first, you draw the figure. Second, you label the current. You have to show the direction and show it through the resistor. So I'm just going to choose, and remember, you're choosing a direction. You could choose a different direction, but in this case it seems logical to put I1 going up because that's the batteries driving it that way. I2 going up because the batteries, this is R1, I didn't label all these, this is R3, and I3 going down. And so usually we start with the junction rule. I1, we go to this node or this junction, and we get that I1 plus I2 equals I3. Or I1 plus I2 plus I3 equals 0. Either way is fine. So that's based on writing the junction rule or the current law for this node or this junction. Now we need two other equations. So we could choose a loop here, we could choose a loop here, or we could choose this loop. So I only have, and turns out we just need two of those. But I'm going to choose the outside loop and this loop, just so we have only one battery in our equation. But you could do the two batteries, but you've got to worry about the direction. So if we choose the outside loop, we're going to have, why don't you write those three loops and come back rather than waste time. Just write the three loop equations and see if you can get them right. Okay, just to remind you, you can put the currents any direction you want, but the equations have to be consistent with your drawing. And if you don't put your currents in there, there's no way of me knowing which direction you're choosing, and the direction is important, as you'll see. So if the direction were different, this equation would be different. But for the ones I've drawn, let's do the outside loop. So we have 25 volts. When you go in the direction of the current, it's negative. 50 ohms I1. Direction of the current, negative 150 ohms I3. All that has to equal 0. Now if we do this loop, we have 49 volts. A voltage drop going in the direction of the current, minus 100 ohms I2. Another voltage drop, minus 150 ohms I3 equals 0. Supposing we did this one. Some of you choose this one and got it right and others didn't. So if we go this way, it's going to be 25 volts, a voltage drop, minus 50 I1. Now we're going around the loop opposite the direction. So the voltage drops this way, it's going to rise this way. So this has to be positive 100 ohms I2 because of the direction we chose. And notice we're going backwards through the battery, so that has to be a negative 49 volts. And that would be equal to 0. So any three of these four equations, 1, 2, 3, 4, could be used to solve the problem. And you were not asked to solve the problem. This is where you ended. Okay, moving on. Number 7 was where you built the circuit and measured the voltages and currents. And most of you did well on that. It was really great that the labs are working. Most of you did well on that. Some of you got the wrong currents because you must have broken the circuit wrong when you put the current in series. That's a tricky part. We'll continue to work on that. The last problem is graphing the RC circuit. Let me spend a little bit of time talking about that, but there were many videos posted on RC circuits, so I'm not going to go into a lot of detail. I'm just going to go quickly over the highlights. Here's the circuit. When we close the switch here, the battery is going to charge the capacitor, sending current through the resistor, and current will flow until the capacitor reaches 12 volts, and then the battery voltage and the capacitor voltage will be equal and opposite, and the circuit will be static, and there'll be no more current in the circuit. So if you think about that, you know that the current is going to start high and decay to 0, because at the end there'll be no current, And the capacitor starts with 0 voltage, so the capacitor has to charge. And so what you should know about these circuits is that there are two behaviors, and only two behaviors, either a quote-unquote charging behavior that charges to some maximum value, or a discharging behavior that discharges from some maximum value. And the shape is like this. So the charging shape has an equation that looks like this, and the discharging shape has an equation that looks like this. The e to the minus t over tau is always going to start at 1 because e to the minus 0, e to the 0 is 1, and as this number gets bigger and bigger, this goes towards 0. So this is going to start at 1 and decay to 0. This is going to start at 1, but since we have 1 minus, it's going to start at 0 and charge as this goes to 0 to the maximum value. So it's good to know there's only two shapes, know there's only two equations, and know how to match the equations to the shape. And the Q can be Q, it can be I, it can be the voltage across the capacitor, it can be any quantity. You just need to, if this is VC, then this would be VC max. If this is IR, this would be IR max, and the same for this. So two shapes and two equations. And if you understand the physics, you'll get the shape and the equation right. Now the rate at which it goes depends on this time constant, right? This is the variable time. This starts at 0 and increases all the way to infinity. This is a constant, and so what you know from your equation sheet, and you should know, is that the time constant is the product of R and C. And if a time constant's big, it will take a long time to charge and discharge. So if you have a big resistor, the current flows slow, and the charging time is long. If you have a big capacitor, it holds a lot of charge. That makes the charging time longer. So you should understand the physics of that. And in this case, in the first charging cycle, the 16 ohm resistor is not in the circuit. And so it's 8 ohms times 8 times 10 to the minus 6. And so you get 6400 microseconds, which is 6.4 milliseconds. That's your time constant. And what you should understand, this is getting into a little more of the detail. When the time reaches the time constant, your e to the minus 1, and e to the minus 1 is about 0.37, which means 1 minus e to the minus 1 is about 0.63. So that means when the time reaches 6.4 microseconds, this will be 63% charged. And after two time constants, it's going to go another 63%, which is about 86%. And after 3, it's about 95% charged. So you do not need to do any calculations when you do these sketches. You just need to, at one time constant, go to about 1/3, 2/3, 1/3, and then in the next interval, another 2/3, 1/3, and so on. And you must label the graphs. So you had to calculate Q max. You had to calculate I max. And you can see what the I max is going to be. I is going to be voltage divided by resistance. So the maximum voltage would be 12 volts divided by 8 ohms. And so the maximum value in the charging cycle was 1.5 amps. In the discharging cycle, you now have 24 ohms of resistance. So the I max in the discharging cycle should have been a half an amp. And the Q max comes from the equation that Q equals C times V. So if you take the C and you take the V, you would have gotten 9,600 microcoulombs, or 9.6 millicoulombs. And so that's where this charges to. And so on your graph, you should have written 9.6 millicoulombs. And you should have all this labeled 6.4, 12.8, with the label of time, with the label of the units, milliseconds. I know this is messy, but that's, and there were videos that go over this slowly and step by step. And some variation of this is certainly going to be on the final exam. So if you're still not confident about your understanding of this, continue to work on it. Okay, we're done. Whoops.